Great, thanks everyone. Thanks for having me here in Cardiff. I'm visiting for the week for this Gas and Galaxies workshop that we've done between Cardiff and U of Illinois. I titled this Death by Black Hole because it sounds cool, right, obviously. And I realize this is the kind of thing that sounds very sci-fi, but inevitably disappointing. Like, there's not going to be actual death by black hole, this thing. And yeah, no humans will be harmed in the black holes of this. But I do promise that there is stuff getting destroyed by black holes in this talk. So not completely out of the question. And so I am interested in studying black holes and also galaxies because we think that these are really connected, even though the scales are really different. And the reason is that we think that in the centers of most galaxies, there is a supermassive black hole. We don't have insight into the black hole directly, right? We can't see any light coming from it, and the light's escaping, but we can usually see that there are black holes because even though nothing's coming out of the black hole itself, the stuff immediately around the black hole is often very, very bright. So let's jump here. It's kind of a movie version of this, of what we think an artist's conception would look like of the immediate surrounds of a black hole. In these, I tried to label all of them as either artist impression or real data, just because sometimes when we look at these or present these images, often it's kind of misleading or hard to tell. This is definitely the pretty artist impression, but I will show some real data as we go. And so what we think is going on in the centers of the galaxies is that you've got gas and dust that's really trying to hit spiral. And as you get gas and dust, that starts to spiral around, hits other gas, hits other dust, and you actually release a lot of light. It seems odd to say, but most of the brightest objects that we can see in our universe are often around black holes. This kind of system, this black hole, is actually better at making light out of matter than our sun is, which seems kind of wild. Our sun is not actually that good at making light out of matter with nuclear fusion. This is actually way better in a way that's kind of surprising. We still don't understand why. So we think these are in the centers of most galaxies, including our own. So I do want to show some real data. So this is data not taken by me, it's taken by the CAC and UCLA Galactic Center group. This kind of data is extremely hard to collect. This is a team that won the Nobel Prize a few years ago for this discovery, for how difficult it was to collect this kind of data. And what we're looking at is a set of images really zoomed in the center of our galaxy. This is zoomed in to the extent that this measure was very difficult, where this scale bar here is in these units we like called arc seconds, where if you think about how well you can kind of resolve stars or tell two stars apart in a sky that's over Cardiff or Illinois, usually our entire kind of blob, even if you had a great telescope, would be about the size of this whole image, right? You really have to refine the image to get something that's good. And they're doing this through using lasers to kind of predict what the sky is doing. And what we see is a ton of stars are all moving. And when we start to track the orbits, we can see that they're kind of buzzing around a place in the sky where there isn't another star. And we can use the same kind of physics that we use in Physics 101 to try to say, all right, this is moving. How much stuff does it take to kind of cause these stars to whip around? It has to be something that weighs a few million times the mass of the sun. But if there was something, a star that was 1 million times the mass of the sun, we would absolutely see it in this image. And it's not there. There is something weirdly bright in the radio that we know about, but it's not a normal star here. And so these motions, the fact that we can kind of zoom in on these, was one of the key pieces of evidence that in our own Milky Way, we have a supermassive black hole in the center. I like this movie because it shows that the real data is messy. You have artifacts, you have to track things, you have noise that's in some nights but not others. And this is taken over, starts in 1998, it goes through 2018, taken over decades. This is usually not the gift that people show. This is the nice cleaned up version of it where you can really see the orbits of the stars. And this is showing really the tracks of where we can find the stars here. They're all going around our center. And some of these stars kind of whip around, and you can see that they get quite close in this image, but they're actually quite safe. Even the one star that kind of goes all the way in and goes all the way out, it's quite safe. These orbits are being tweaked a little bit by the fact that we've got Einstein's relativity and all of that. but most of these are orbiting basically just like the Earth orbits the Sun. This star, though, could potentially be much more unlucky. The star that's kind of zooming in and zooming out is whipping past with a ton of energy, it's kind of slingshotting back out, but if it did get close enough, it wouldn't necessarily get sucked into the black hole, but it would get close enough that we would have different physics. So if that star got close enough, it wouldn't necessarily get sucked in unless it kind of directly hit it. If it got just close enough, what we'd start to have to worry about as physicists is tides. So every time I mention this, I hear the cool stories about the tides that you get in Cardiff Bay, where you've got these extreme tides. And it's exactly the same physics as what causes the tides on the Earth's oceans from the moon. Right? The moon is pulling more on one side than the other on the planet. This is the same physics that has Jupiter kind of messing up its planet of Io, where Io gets all this cool volcanic activity from that. As the star gets really close, the black hole is pulling more on one side than the other, and that difference in force, the fact that one side is getting pulled a little bit more than the other, if that difference is enough, it can just tear the star apart. And this is the artist's conception of what that winds up looking like. You have a star that comes in, it tears off a little piece of it, that's the whole thing, and all the stuff that used to be part of the star, that now doesn't have all of that slingshot energy and will fall into the black hole. This kind of thing is something that we think that we're able to see, right? Stars that are getting tidally shredded or spaghettified by these black holes is something that we think that we can see in real data now. This shouldn't happen very often. For example, we saw all those nice stable orbits in our own Milky Way. But if we waited maybe 10,000 years, we would maybe see something like that in our galaxy. As astronomers, we often play the long game, but maybe not 10,000 years. So fortunately, we can look in other galaxies and try to see this kind of thing should happen. We can predict it. Do we see anything that looks like this? And we can make predictions and say, all right, it should look like the black hole has some luminosity, and then it goes away over some time scales that we can work out with some math. It should be maybe a few months. And we think that we can see something like this. So I've got a set of little movies that come from this really nice movie that was created by Desi as part of the day release. And this is meant to show kind of the different ways this might happen. So at the start, we have a star coming in. And we think for this to happen, usually the orbit isn't nice and circular. Usually it's kind of a really wild, kind of very eccentric orbit. And as that star gets closer, it starts to just be tidally pulled, where this is what the actual shape of the star should look like when this happens. It should be physically elongated as this is happening. Stars don't like this, right? The gravity holding the star together is getting wildly confused, and what's happening with the fusion of the star, it could be totally wild. But it starts to stretch, and as I get to that closest point with the black hole, it will potentially kind of unbound the entire portion of the star. So this is the kind of pretty artist version of what this looks like. And this artist version isn't coming out of nowhere. This is motivated by people who are doing supercomputer simulations of this kind of thing. You put in a bunch of particles at your star, you set up kind of your general relativity for your black hole, you send stuff in. And this kind of video is inspired by some of those simulations. And so a bunch of that material will kind of come back, and in this version you get these jets of stuff coming out. The reason that this kind of thing is tricky for people to model supercomputers is that what's making those jets come out is what every physics astronomer hates me asking about, which is there's magnetic fields and all of this. They're doing. The magnetic fields are making all this really difficult to calculate, but maybe driving these little jets. And so this shows the whole movie as it goes, showing kind of the formation of all of that. So this is what we expect should happen some of the time. You should have these black holes in the centers of most galaxies, and there might be some gas and dust around. For example, like our black hole doesn't really have a lot of gas and dust around, others have more. And eventually, if you wait long enough, a star should maybe get into one of these orbits, be tidally stretched, get completely disrupted. And we call this kind of event, when it should happen, a tidal disruption event, or sometimes TDE, because we love acronyms. And this kind of event should be extremely bright. And that's the best kind of prediction to make. This should happen, and it should be bright, because it means we should go out and look for it. And so I want to talk about how we try to find these with real data, with telescopes. And the entire game for this is to look for something that's changing on the sky. So what we'd like to do is to take a telescope, and instead of looking at specific galaxies that we think, okay, this is the galaxy that will have one, this is my interesting galaxy for this test, to take images of as much of the sky as we can, and then go back and take images again, and go back and go back and go back, and then look for things that change. This is something that we often do in collaboration with other astronomers who have a similar test to see what they need. So this kind of strategy is how people find supernovae. This is how we find things like near-Earth asteroids that we have to worry about. A lot of the technology that goes into this comes from the fact that it is really nice to think that we know all the near-Earth asteroids that could potentially cross Earth's orbit. So there's a lot of effort that goes into mapping all of that, and a lot of this can be found almost incidentally as part of that. So this is the game that we try to play. We have, say, an old image, and we go back as often as we can, and at night, and take a new image, take the new one minus the old one, and ask, is there anything new? So this is a real data where you can see the galaxy, you see some stars, and the image is a little bit different, but when we look for anything new, there's really nothing there. That suggests that this is working pretty well. There's not something there when there shouldn't be, but when we do this kind of experiment, most of the sky looks like this. It's boring, we sit through it. What we're looking for is something like this. We've got this old image, and we take a new image, and when we subtract off that old image, there's something that remains. There's something new in the middle of this galaxy that wasn't there before. In this case, you can sort of see the scale. This is pretty bright compared to the rest of the galaxy. There's something very bright. The center is doubled in brightness over a few weeks, a few months. That means that it's quite interesting, that we want to figure out what is that new thing. That new thing is probably not something like an asteroid, because we would see that kind of going through the field. It wouldn't be in the middle of the galaxy. Could be a supernova, something else. And so what we do is we take, all right, this galaxy has something new, and we want more information about the light. We take the light and we spread it into its wavelengths, we look at its color, and we say, what is this thing? So this is an example of this. This is more real data for one of these cool events, where we had some data about how bright that object was as a function of its color or its wavelength. And the one in yellow was some data taken in 2007, and the one in blue was in 2014. And you see something changed, right? Something appeared in this galaxy and it was very blue. And we can use these different features to say something about the nature of the temperature of the event and that kind of thing. And so where we are as far as finding these, we have found some of these. And we found almost 100 so far. This timeline is really accelerating, such that if you've heard about this before, that's fantastic. I love when this is featured. But if you're like, this appeared out of nowhere, why is everyone talking about this? It's kind of, that's what's happening. Until 2019, there was a few of these. Maybe there's 2 discovered every year. It was very exciting when it did. We find a new one and someone would post it, and we try to point a telescope at it, etc. But in the past 5 years, our surveys for this kind of thing have been growing, getting better at this technology. And now we're finding a few dozen of these per year. It's the case where we can study these, and I can collaborate with people on paper, and we can put 12 of these in a paper and not have to write special little papers about each one. This is great. We can do a lot of cool science with this. But we're at another inflection point that will happen really imminently. And that's that we starting this year and certainly next year, there's a new facility called the Rubin Observatory that's going to do this sort of experiment where you look at the sky and kind of come back to it and look at things that are different on a scale that we just have not been able to do before. This telescope is an 8-meter telescope, right? Most of these so far are quite small. This is the kind of thing that you do with a small telescope kind of in between other people's programs. This is a dedicated experiment. This is the astronomers kind of stealing some techniques from the physicists as far as having one big experiment and working on it. The camera on this is phenomenal. I've got an image of it in a second. And this kind of thing should find thousands of these stars being shredded by black holes, like these, every year. Any kind of phenomenon that changes on the sky Rubin is going to find an immense number of them. Supernovae, asteroids, variable stars, anything. It's definitely a huge data challenge, and there's a lot of work that goes into light hits the mirror of Rubin, so we do science, but it's a really cool opportunity to really do this kind of thing at a huge scale. And this is happening now. This telescope exists. It's commissioning literally as we speak. And the reason that I'm showing pictures of the telescope and not pictures of the data is that that's something that we can all see on Monday, right? I've been talking about this for feels like forever, but actual data, the first public data images that will come out, are coming out on Monday. So I came at the wrong week, but we'll have some work to do once the data comes in 2 weeks. But keep an eye out. If you see a thing on space news that's this picture and talking about the observatory, that's this, right? That's going to find all of these cool and variable events. And there's a huge team of people that's actively commissioning it, making sure that mirrors work, the camera works, and really getting ready for this experiment. And so this is a nice time lapse of the thing during commissioning, observing, and this is sped up. But this telescope, right, that the diameter of kind of this part of the mirror is 8 meters. This is the behemoth of a building, and it turns to look at new fields, terrifyingly fast. It's you have to wear hard hats and stuff to be in this. But I would not really want to stand around the world this building goes shoo. It's really kind of scary to watch the non-sped up things. And it's extremely fast. It's extremely efficient, and that's why it's going to do such good science. I like this comparison of the camera that's on this, because it's not just a large telescope, it's a telescope that's got extremely fast optics, it's got a huge field of view. And so this is, for scale, what the camera looks like compared to the full moon, right? This is a massive piece of the sky. That means that it can get a deep image of the entire sky basically every 3 days. It's 3,200 megapixels, which for comparison with your regular nice camera would be 12 to 50. If you wanted to display an image on 4K TVs in real size, you would cover, this is an analogy made for a US audience. You cover a basketball court with it. I don't know what the appropriate camera is. Bigger than this room. It would be bigger than this room, but 4K TVs on the floor. It's an impressive camera, and it's going to do a lot of cool science. All right, so that's enough of me talking. I'm happy to answer any questions on this and other related things. Yeah, thanks again for coming.
Are there any other things that can count for the changes in brightness and the wavelengths of light? And if so, how do you limit it?
Yeah, that's a great question, and we spend a lot of time trying to answer this. So one of our main things that might look like this, might look like a star being disrupted, is actually just a bunch of gas coming in. Especially it kind of comes in a clump from some kind of weird event. And the main thing that helps us is to get this data where we look at how bright it is versus wavelength. Because it really will look different if it's gas versus a star, because the composition will be different. The thing that's sort of good and bad about that is that with Rubin, with this new facility, we won't be able to get that kind of data for thousands of these. So we try to make do with less data. And usually if it's a star, you kind of get one flare from the star and then it dies off as that material kind of goes in. If it's gas, there's usually a supply of, if there's some gas, there's more gas where that came from. And usually you'll get something that kind of putters along for a while. And if we have enough data, we can kind of tell the difference between those. But it's definitely something we try to work out of how often should that happen? What should it look like when it does? And is that doing something that kind of biases us in some way?
I have a bit of a silly question. You mentioned that there's a data release next week and there's pictures involved. Do you know what of? Is it tidal disruption events, or is it, like you mentioned, supernovae and meteorites and stuff?
Oh yeah, so the pictures that are being released, it's all public. So the pictures that are being released on Monday are going to be basically example images of this. And so they've picked parts of the sky that are we can look at repeatedly with a lot of facilities. So it's really useful to look sort of in the poles of the galaxy and the poles of the Earth, where that kind of overlaps, because there's places where something like the Hubble Space Telescope can look at all of the time, and this can look at, you know, most of the time, right? And so that kind of thing has been well studied by a lot of different instruments, and so that's, if people have like a favorite field, a favorite deep field, those kind of parts of the sky are often advantageous where you can look at it, it's away from the galaxy. There's also some things within the galaxy for people who look at stuff in the galaxy, stars. And so what will be released is these images. The thing that will take a lot of work to go from these images to the TDs will be that differencing. And that will take us a while. That data will start to get released the following week, but we'll have to kind of improve it as we go.
Looking forward to it. Let's keep our eyes peeled for that, don't we? Yes.
Will the photos and data be open access for scientists to use, like at will, or will it be something that's being commissioned by like a group, a specific group?
Yeah, so it's being commissioned by a group, there's a set of countries that have bought access, and then a set of countries where individual scientists have bought access. But then after a given time, all of the data will become public and public data releases. So it's sort of a tiered thing, and then eventually will all be public.
Give it for Tesla one.